After challenging your minds with the augmented matrices for the last two classes, you may find that this topic today seems a little easier. Because today we're strictly about how do you do arithmetic on matrices. We're back to normal matrix operations now. We need to basically figure out how does one add, subtract, and multiply. Of course, you're already out there going, yeah, because you can't divide a matrix. And that's absolutely correct. You can't divide matrices, but we will solve that issue with something else in our next lesson. But today it's strictly, can you do basic operations? Okay, the first thing here, if you notice, I have a 4 in front of a matrix and a -3 in front of a matrix. What is it I want you to do with that? Well, when there's a number in front, that's called scalar multiplication, because when you multiply by a single constant number, that's a scalar. Those are called scalars. So we're scalar multiplication, and yes, it's exactly what it looks like. They simply want you to multiply through and take every single number in the matrix times 4. Each number in the matrix is called an element. So every individual number is an element. Now in this case, we also need to remember, when is it possible to do addition and subtraction? In this case, can I combine this matrix together? Because you'll notice the two matrices don't have the same number of elements. And hopefully somebody's out there going, yes, you have to check the dimensions. So the next question was, what were the dimensions of a matrix? The dimensions are always given as the number of rows by the number of columns. So, how many rows does this first matrix have? Well, it's got 2 rows going across. By how many columns, vertical columns? By 3. So it's a 2 by 3 matrix. The second one has 2 rows also, but it has 4 columns. Okay, that means, can we actually add and subtract these matrices? And hopefully somebody out there is remembering and screaming, no, 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 you can't. That's impossible. And you would be correct, because to do addition or subtraction of matrices, your matrices must have the same dimensions. So if they do not have the same dimensions, there is no answer. You can't go adding extra numbers to one of them, so you can. This one is strictly a not possible situation. You cannot add those two matrices together. Cannot be combined with addition and subtraction. Okay, so we are going to, however, take it here, and I'm going to see if I can shortcut since whoops, that didn't work. Try that a little differently. I'm going to see here if I can manage to copy and paste this thing, and then by miracle of miracles, woohoo, yeah, baby, get it to move so that I don't have to rewrite all these numbers. And we can indeed be pleased to see that, yes, we can. And so now I'm going to alter this problem by simply cheating, knocking off that back column of numbers, and saying that, okay, now, these are our two matrices. Are these two able to be added and subtracted? And the answer is definitely yes, because they have the same dimensions. So now it's just simple arithmetic. You're going to multiply all the first matrix by 4. So we're going to get 8, negative 12, 16, 24, 0, and 20. No problem there. Okay, on the second one, here's your choice you have to make. Do you want to distribute the 3 and leave the subtraction sign? Or do you want to change it to addition? I find students make more errors if they leave the subtraction, so I'm going to strongly encourage you change it to addition. I think that will make it easier, and then we are distributing -3. So we're going to have -15, -21, +6, -24, -18, and -15. That way, we've already taken care of the negative and we don't have to worry about losing it. Now, last but not least, we simply need to add them together. And how do you know which numbers to add? Well, it's common sense. You add the numbers in corresponding locations. So you add the first number to the first number. You add the second number to the second number. You add the third number to the third number, etc. So 8 and -15 makes -7. Going across, -12 and -21 would be -33. 16 and 6 makes 22. 24 plus -24 is a 0. 0 plus -18 is -18. And 20 plus -15 is 5. And ta-da, you have combined your matrices together. So matrix addition and subtraction, not a big deal. So let's move to where it gets a little more exciting. Let's go multiply. Okay, now here's the question. With multiplication, do they still have to have the same dimensions? And the answer is absolutely not. Only if they were perfectly square, 2 by 2, 3 by 3, would multiplication even be possible. Because if you will recall, you take the rows of the first matrix times the columns of the second matrix. So therefore, if you are going to come across the row of the first one, there are 4 numbers coming across. You're going down the column of the second one. And so we're going to have, we have to have the same number of numbers there. 4 going across, we got to have 4 going down. Now, in terms of your dimensions, what that means, if you check your dimensions in this problem, in this particular problem, we have, the first one is 2 rows by 4 columns, and the second one is a 4 rows by 2 column. And if you'll recall, the key factor that has to be true is the middle numbers, it was those 4s, must be the same. So as long as those 2 are the same, or if you can visually count 4 across, 4 down, you know your matrix multiplication is going to work. The other interesting feature to this is your final answer is also given to you in this problem. Your final answer is given to you by those the first dimension and the last dimension. So in this case, our final dimensions, it's going to be a 2 by 2. So when we get done, this answer will result in a 2 by 2 matrix. So your answer matrix does not have to look like either of your starting matrices. Okay, so if we do that then, now we're ready to multiply. This is not a difficult process, it just requires you to be very careful with what you do. So that's a key. Excuse me a moment, trying to move that matrix down a little bit. So we have plenty of room here. Here we go. We're going across. I'm going to attempt to color code this baby for you. And so what you're going to do is you are going to take, if you recall, you take the first number times the first number. You take the second number in the row times the second number in the column. Then you take the third number in the row times the third number in the column. And lastly, you take the fourth number in the row times the fourth number in the column. Okay, you multiply those corresponding terms. So we're going to do that here. First numbers made 40. Second numbers would be 0. The yellow numbers would be -9. And the white numbers would be 8. Now, those aren't separate numbers. Instead, what you do is you add all of them together. And that gives you one answer in your resulting matrix. So in our resulting matrix, if I add all those up, I have 39 as my total for all of those. So I've only got one number out of that whole multiplication. Now you have to take each row times every column. So now we've done the top row times the first column. You have to continue to do the top row times all the additional columns. So if I'm going to do top row now, I'm going to go hit the second column comes next, doing the same thing. So first numbers times first numbers. And hang on a sec here. I have no idea what color I've got. Let's do bright green. Will work. Okay, so I'm doing first number, oops, sorry. First number times first number, which will give me what? Hopefully somebody out there said negative 15. That's not black. Actually, that's okay. We'll do that in white. Negative 15 plus second number times second number. So now I'm taking negative 2 times the second number in that column, which would be a positive 2, plus, now I'm going to go back and do third number, the 1, times the third number in the column, which is the 5. So that's going to make a total of 5. And then last but not least, I'm going to do fourth number, the 4, times the fourth number here, which is also a 4. Got lots of 4s, and so we get a grand total of 16. Now, add all those together, and that's going to add up to 8. So my resulting answer for that one is 8. Now, how did I know to end my matrix? Well, for two reasons. I have now taken the top row times every single column, and the fact that I know this answer is going to be a 2 by 2. So if I now go, I have to move to the second column. So now I'm going down a row here. I now have to take the second row times the first column. So what I'm doing here, I'm taking first number in the row, second row, times first number in the first column. And so if I do that, 3 times 8 is going to give me 24, plus, now when I do second numbers, 6 and times 0 gives me 0, plus third numbers, negative 1 and negative 9, which will give me a positive 9. And then last but not least, if I do third numbers, I'm going to have 7 times 2, and that's going to give me 14. Add all those together, I got 33, 43, 47, and so my answer there would be 47. Okay, am I done? Well, of course not. I got this gap over here, so I can't possibly be done. I've got one more column to go, and so I am now going to take the bottom row times, I'm doing bottom row, second column. Second row times second column. And same thing, first number times first number is going to give me negative 9, plus second number times second number is going to give me negative 6, plus third number times third number, negative 1 times positive 5 is going to give me negative 5, plus fourth number times fourth number, 7 times 4, which would be 28. Out of space there. And if I add all those together, that's negative 15, negative 20, plus 28 is going to give me a nice round 8 again. And there would be my final answer. And notice, yes, indeed, it is a 2 by 2. So let me play a few games with you here a moment, off to the side. If I told you you were going to take a 4 by 7 times by a 7 by 9, A, is it possible? Yes, because the 7s are the same. And B, what's the resulting matrix going to be? Yes, indeed, it's going to be a 4 by 9. Now, what if I mixed it up on you a little bit and I said the resulting matrix is going to be a 5 by 11? What would I have to have as dimensions, or can you name me some dimensions that would give me a 5 by 11 answer? Well, the key thing is, where do I know the 5 and the 11 have to go? The 5 has to be the first number in the opening matrix, and it's got to be the last number in the second matrix. And what do I know about the 2 in the middle? I know they've got to be the same, so you can pick virtually any number you like. It could be a 5 by 3 and a 3 by 11. It could be a 5 by 9 and a 9 by 11, but that's going to give me a 5 by 11 answer. So you can always predict what you're going to get. Okay, this last one here looks a little funky because there's hardly anything there. There's just one column, one row. Okay, first question, is this a possible matrix? Can I multiply these together? And hold on a second, I want to move this up. I'm going to need to squeeze one more on here, I see. So, big question is, check your dimensions. Here I have 4 rows by 1 column. Here I have a 1 row by 2 column. So is this possible? These are such puny little matrices. But yeah, since my ones are the same, it's going to work, and my answer is going to be a 4 by 2. So my answer is going to have 4 rows and 2 columns. My answer is going to be huge, but this little matrix looks like no way could this happen with the initial. Now, it's also a very easy matrix to multiply, because now we are simply doing, okay, rows by columns. So how many numbers are there to multiply? And if you're screaming, well, yeah, there's only, I should have done that in a color. You can see, it will stay there. There's only 1 number across and 1 number down, so woo-wee, this is a tough one. So doing the first one, first number times first number, that's it, I get a 2. Take the top row times the second column, I get a 3. Boy, this is going to be very difficult. Okay, next one. First row or second row times first column. 7 times 2 is 14. And then if I do next one, 7 times second column, 7 times 3 gives me 21. And I keep going. If I take the 8 times the first column of 2, I'm going to get 16. 8 times the second column of 3, I'm going to get 24. And then last but not least, if I take 4 times the 2 going down, I'm going to have 8. Then I take the 4 times the 3 and I get 12. And there is indeed my 4 by 2 answer. Now, that looked like a lot of fun. I didn't even have to add anything up. Some of these can be nice. Some of these can be challenging. Okay, last then, you're going to have some problems where they actually get you to look at the real-world uses of matrices. Imagine that, real-world uses. So we have here Q-Ball Incorporated. They make 2 pool tables for home, commercial, and professional use. The amount of time required to pack, load, and install each type of pool table is summarized in the matrix T down here for time. And all the times are in hours. So in other words, if you read matrix T, top left corner, a home pool table takes 1 hour to pack, 0.2 of an hour to load, and 1.5 hours to install. A commercial pool table takes 1.5 hours to pack, half an hour to load, and 2.2 hours to install. And of course, professionals look like they take even longer because you have to do a more quality job, make sure they're more level. So that's the amount of time it's going to take. In this case, the company has 2 warehouses. They have one on the West Coast and they have one on the Midwest. And these are telling you the costs. Need to emphasize that. This is the cost. Here, this is the cost of what you're paying per hour for people to do this. So this is the cost per hour. So this is $10 per hour. You have to pay the packing people $12 per hour and $13.50 per hour. Now, why aren't these numbers the same? Well, prices for what you're paid are different on the West Coast, and also what it costs you to live on the West Coast. It's all higher. It's cheaper to live in the Midwest, but we also don't earn as big salaries either. So in this case then, they have several questions here. First one is, what's the cost to pack, load, and install a commercial pool table from the coastal warehouse? So they just want you to common sense this. The coastal one, all right, so we need to know what's it costing. It's at a commercial pool table. So we're doing the commercial row, and we want pack, load, and install from the West Coast. So commercial, it takes 1.5 hours to pack it, but we're paying $10 an hour. Plus, it takes half an hour to load it at $12 an hour. Plus, it's going to take 2.2 hours to install, paying $13.50 an hour. Okay, so yes, we can figure that out by hand, but wasn't that kind of annoying? Because that's going to be $15 plus $6, excuse me, plus, that last one's not so obvious. So we're going to pay $50.70 to pack, load, and install this baby. Okay, they also want to know what it costs in the Midwest for a commercial, but do you really want to have to do that again? Because then we'd have to go back and go, okay, if we're in the Midwest, then we'd have to take, still a commercial one though, so it's 1.5 hours times the $8 an hour, plus half an hour times the $10.50 an hour, plus 2.2 hours times $12.50 an hour. Okay. Well, obviously, this one isn't going to cost as much. So, excuse me, we're going to do, my fast fingers are trying here. 1.5 times 8 plus 1/2 times 10.5 plus, oops. That's what I get every time I try to type fast. Minor error there. Didn't think that looked so good. $44.75. So costs less. But wouldn't there be a better way than having to find the right line in the right chart to do it? Well, they want you to actually then multiply the entire matrices together and see what you get. Okay. This is not going to be great fun by hand. You can do it, but not great fun. But we're also going to let our calculators do a lot of our matrix operations. So we're going to kick over to our calculators and punch this in. In fact, I've already punched half of it in just to speed this up. I've put this first matrix in already. I'll show you how to put a matrix in again. Okay, but first I need to come out here and say times. So I'm going to multiply the second matrix. When you want to put a matrix in, obvious choices, menu. Where do you suppose we go from there? Well, yes, number 7 says matrix. So we're going to do that one. And then number 1 choice, we are creating a matrix. So we're going to hit create. And wants to know what kind of a matrix do you want to create. We are just doing ordinary matrices right now. And so I needed this second one. If you looked at it, it had 3 rows and 2 columns. So I'm going to up that to 3 rows and 2 columns. Okay, and then you simply type the numbers in, and if you recall, if you hit tab, it will go across the row. So I'm hitting tab, it's going over. I hit tab again, it goes down to the second row, and those are 12 and 10.5. And my third row is 13.5 and 12.5. Okay, now, they told me to take T times C, the time times the cost. Why did it have to be that way? Why couldn't I have reversed the order here? And I wish I could draw on this, but I don't believe it'll let me. So you have to remember you're going across the rows. So if I go across the rows, I got 3 going across, I need 3 going down. So this one works. But if I had reversed them, I would have 2 going across times 3 going down. That does not work. So it's really essential when you do matrix multiplication that you actually pay attention to what order you're multiplying in and make sure that it's possible. So I'm going to hit enter, and it's going to tell us all these lovely answers. And unfortunately, I foolishly didn't copy these down, and I really want them on the other page, so you're going to have to bear with me a moment as I go back and forth. 32.65, 50.7. And so the result of T times C was 32.65, 50.7, and I just lost the last one, but we'll go back and get it. 60.25, 28.85. And this is when I miss people to read me numbers. And last but not least, 44.75 and 53.125. Now, the bigger question is, what on earth do those numbers mean? Okay, they're random numbers, and that's the problem I have with people catching what it actually means when they do these problems. Okay, notice here we took matrix T times matrix C. And we took matrix T, we took the rows of matrix T times the columns of matrix C. What do the two of them have in common? Realize we were going across the first matrix. So we were taking the pack, the load, and the install. We were going down the second matrix. I want a different color. I see I used that color twice. So if I'm going across here, pack, load, and install. If I'm going this one, I took pack, load, and install times the cost of pack, loading, and installing. So doesn't that make perfect sense? So that's what I wanted to multiply those together. And so consequently then, the other labels are simply what was still there. So that means since I multiplied the pack, load, installs, that means going vertically, I've still got home, commercial, and professional. And going across then, would be coastal and Midwest. So what's it telling you? By doing the entire matrix multiplication, we just found out that the home and the cost, the cost for the full installation of a home pool table is $32.65 if you're on the West Coast. It's $28.85 if you came out of the Midwest warehouse. So then if I said, so what does it cost to have a professional pool table installed in the Midwest region? Yeah, you'd say $53 and 12.5 cents to be specific. So we can, once we find those things out, we just got all that done very, very quickly by multiplying our matrices together, rather than what I did up there at top to figure those. That was annoying. I had to multiply all that out. Here, I see the exact same answers I looked up there, but much more quickly and efficiently done, particularly if you use a calculator. Okay, next time then we're going to actually solve equations using matrix equations. You may remember that's a hugely powerful function. So you can look forward to that one. We'll be doing some by hand and some by calculator. Be sure you read on today's assignment which problems you must do by hand and which ones are allowed to do by calculator. Good luck.